Okay, in this lecture I am going to start the Huckel molecular orbital method. Huckel's molecular orbital method. As I told you in the last lecture that Huckel molecular orbital method, HMO method is a semi-empirical method, is basically a semi-empirical method where some of the two electron integrals are ignored, and to fit with the experimental data some parameters are included, okay, like that. HMO method is a semi-empirical method, and HMO method, right, is applicable only for pi electrons present in the molecule, only for pi electrons. It is not applicable for sigma electrons. Okay, so this is the basic assumption, basic information about Huckel molecular orbital method. Now, what are the assumptions that Huckel made? Okay, before going to that, let me give one more information here. This method was actually introduced by Erich Huckel, Professor Erich Huckel. Okay, he introduced this method just to make the calculation easy. Okay, and he proposed this method to compare, okay, stabilities of the molecules containing pi electrons. Okay, and you can also calculate the energy difference between HOMO and LUMO levels, right? And some comparison we can make using this Erich Huckel method. Okay, yeah, he made a lot of assumptions, okay, just to make the calculation simple. That is why the Huckel molecular orbital method is often called as a simple method. Okay, why it is simple? Because Erich Huckel considered or introduced lot of approximations, right? Yeah, we will discuss all those things as we go along, right? Before first let me introduce assumptions. What are the assumptions that Huckel made, okay, in the Huckel molecular orbital treatment? The first assumption is that suppose if you have an organic molecule, okay, if organic molecule containing pi electrons is given, okay, if you take an organic molecule containing pi electrons, okay, we know very well the pi electrons are usually we say that it is delocalized, whereas sigma electrons are localized. Okay, so people assumed that, Huckel also assumed that the interaction between pi electrons and sigma electrons in a molecule is very weak. Okay, so interaction between sigma electrons and pi electrons, okay, is generally weak. Since the interaction is weak, you can separate the sigma electrons and pi electron, and you can treat them separately. Okay, so what Huckel did was Huckel treated pi electrons separately. So sigma pi separation means sigma electron and pi electrons are treated separately. Sigma pi separation is the first assumption that is made in Huckel molecular orbital treatment. Sigma pi separation, meaning sigma electrons and pi electrons are treated separately. Okay, and in Huckel method, okay, in Huckel molecular orbital method, right, Huckel molecular orbital method treats only the pi electrons present in the molecule. pi electrons of the molecule. Okay, the presence of sigma electrons and presence of the nuclei and other interactions are incorporated in an indirect manner. Okay, so Huckel molecular orbital method treats only the pi electrons of the molecule. Okay, then another important point here is the assumption. Okay, these are all few assumptions that Huckel made. Third assumption is that the molecules containing conjugated pi bonds, okay, if pi bonds are conjugated, then the molecule is assumed to be planar. Okay, so molecule containing conjugated pi bonds are assumed to be planar, are assumed to be planar. Okay, or we can say in the other manner, that is sigma bonds, right? Sigma bonds of the molecule, right, exist in a plane. Sigma bonds, right, of a molecule, sigma bonds of a molecule exists in a plane, and that plane is usually considered as XY plane. Okay, all sigma bonds of the molecule are present in a plane. That plane is considered as XY plane. Okay, and another important information here is, listen, since we have conjugated pi bonds means we have carbon-carbon double bond, then single bond, then carbon-carbon double bond, like that. Okay, since we have a single bond in between two double bonds, there is a possibility of two isomers. Okay, two isomers are possible here. What are the two isomers? One is S-cis conformation, S-cis, and the other one is S-trans. Okay, in Huckel molecular orbital treatment, S-cis, S-trans structures are not considered. Okay, there is no difference is made, okay, for S-cis and S-trans here. It is simply considered as a conjugated system, that's all. Okay, whether it is a S-cis or a S-trans, right, those informations are not considered in Huckel molecular orbital method. So S-cis, S-trans structures are not considered, right? The molecule is assumed to be planar, right, and all pi electrons are freely moving, right, from one end of the molecule to the other end of the molecule, right? It is completely delocalized, right? Then this is third important assumption that Huckel made. Then fourth assumption is that the pi electrons of a molecule, they are all assumed to be independent. Pi electrons, right, of a molecule, pi electrons of a molecule are assumed to be independent. That means the interaction between electrons are not considered. Okay, there is the electron repulsion. Okay, the interaction between the electrons are not considered here. Okay, so under this assumption, we can write the total pi electron Hamiltonian, that is Hamiltonian for all the pi electrons. This can be separated into 1 electron Hamiltonians. Okay, see, this is 1 electron Hamiltonian. We call it as effective 1 electron Hamiltonian for electron 1, effective 1 electron Hamiltonian for electron 2, effective 1 electron Hamiltonian for electron 3, etc., etc. These are all pi electrons. this separation is possible only if the electrons are independent. Or I can write simply this as summation. I'll give some number for this, r equal to 1 to number of pi electrons present in the system into effective Hamiltonian, okay, for the rth electron. So these are all effective Hamiltonian. What is meant by effective Hamiltonian here? What is the meaning? The meaning is that the Hamiltonian for the rth electron, okay, in the presence of all the sigma bonds and all the nuclei and all non-bonding electrons. I repeat, the effective Hamiltonian for the rth electron, okay, why it is called effective? Because this Hamiltonian, right, involves the interaction of all the sigma electrons, all the nuclei and all non-bonding electrons with that pi electron. Okay, all those things are incorporated here. That is why it is called effective one electron Hamiltonian. I'll repeat, this is one electron Hamiltonian. One electron Hamiltonian. Okay, whereas this one is the total Hamiltonian for all the pi electrons. Okay, so total Hamiltonian can be separated into one electron Hamiltonians. Right? This separation is possible only if the electrons are independent. Then, since the electrons are independent, we can also make one more assumption. What is that assumption? The assumption is that the wave function for the pi electrons, the total wave function for all the pi electrons, can be written as the product of, okay, product of one electron wave function for each molecular orbital. So this is a wave function for one molecular orbital, this is wave function for another molecular orbital, wave function for another molecular orbital, like that. Okay, it is a product of one electron wave functions of each and every molecular orbital. So electron 1 is present here, electron 2 is present here, electron 3 is present, like that. Okay, to start with, let us not consider about the spin of the electron and the antisymmetric nature of the wave functions and all. Okay, right? Even if you include the spin and the antisymmetric nature, the calculation remains the same. So you need not worry about that. Okay, so what is psi 1, psi 2, psi 3 here? Psi 1, psi 2, psi 3 are molecular orbitals, one electron wave functions, right, of the molecular orbitals. So I can write this as pi into psi j, where j goes from 1 to number of carbon atoms present in the molecule. Okay, number of carbon atoms which shares the atomic orbital, right? The electrons of the atomic orbital in the pi framework. Okay, so psi j is called the molecular orbital wave function. Molecular orbital wave function. See, you can separate the one electron wave functions like this. The product of all the one electron wave functions, right, is considered as the total wave function. Right? Yeah, this is for electron 1, this is for electron 2, this is for electron 3. Okay, so if you multiply all this, I'll get the total wave function. Okay, then. So this is another important assumption that Huckel made here. Now, the effective Hamiltonian for one electron. Okay, this one electron effective Hamiltonian. The explicit form of this Hamiltonian, explicit form of the Hamiltonian is not known. What is the exact form of the Hamiltonian? That is not known. Okay, so in Huckel molecular orbital treatment, you need not worry about what is the exact form of this Hamiltonian. Okay, so this is not considered, or the exact form of this Hamiltonian is not considered. This is not considered in Huckel's calculation, in Huckel's treatment. It is simply an Hamiltonian, that's all. You need not worry about what is the exact form of that Hamiltonian, right? So if you need not worry about the one electron effective Hamiltonian, so this is not known completely, then what we have to do to find the energy of each molecular orbital, at least you must know the wave function. Okay, if you know the wave functions for each molecular orbital, then even if you don't know the Hamiltonian, you can calculate the energy by using variation technique or other techniques. So the next important assumption that Huckel made is that how to get the wave function for jth molecular orbital. For this, Huckel used the LCAO approximation. Okay, so LCAO approximation, linear combination of atomic orbital approximation, LCAO approximation is used to construct the molecular orbital wave function psi j. So each molecular orbital wave function psi j is constructed using linear combination of atomic orbitals. Okay, so let's discuss some more information on this. What is meant by linear combination of atomic orbital and how to construct the molecular orbital wave function. Suppose assume that I have a organic molecule containing pi electrons. Okay, so let us assume that these are all carbon atoms present. Okay, I have a lot of carbon atoms, and all the sigma bonds are considered to exist in a plane, and that plane is usually taken as xy plane. In Huckel molecular orbital method, the sigma framework of the molecule, right, must be assumed to exist in a plane, and that plane is considered as xy plane. And each carbon atom which are involved in the delocalization of pi electrons, okay, each carbon atom has a p orbital. Okay, each carbon atom has a p orbital. This is the upper lobe and this is the downward lobe, upper lobe and downward lobe here. Okay, right, each carbon atom has a p orbital which has lobes perpendicular to the plane, through this xy plane, and each p orbital has one electron. These are all actually 2pz atomic orbitals of carbon. They are all 2pz atomic orbitals of carbon. Okay, let us start with the carbon atoms first. Assume that the conjugation, pi electron conjugation, exists only between carbon atoms. Okay, as we go along, we'll introduce the heteroatoms also. Okay, so these are all 2pz atomic orbitals of carbon atoms, right? Now these the wave functions of these 2pz orbitals are represented as phi1, phi2, phi3, etc. So these are all wave functions. phi1, phi2, phi3, phi4, etc. are wave functions for the 2pz atomic orbital of carbon atoms. Now what I'm going to do, you all know that according to LCAO approximation, when two atomic orbital combines, you will get two molecular orbitals. Okay, so number of molecular orbitals, right, or pi molecular orbital in this case, number of pi molecular orbitals that are formed, right, is equal to number of 2pz atomic orbitals that combine in LCAO. Okay, so how many atomic orbitals combines, that many number of molecular orbitals are formed. Okay, so this is the idea. Now see, for example, I have phi1 atomic orbital, phi2 atomic orbital, phi3 atomic orbital. Like that I have many atomic orbitals. What I'm going to do, I'm going to take the linear combination. How to take the linear combination? Very simple. You multiply each of these atomic orbital function with the coefficient. For jth molecular orbital, suppose I'll take some jth molecular orbital. For jth molecular orbital, we represent the coefficients like this. C coefficient for jth molecular orbital with atomic orbital 1, coefficient for jth molecular orbital with atomic orbital 2, Cj 3 plus etc. etc. This is how we write the linear combination of atomic orbitals that form molecular orbital. So the wave functions for each molecular orbital, right, are constructed using LCAO approximation. Here remember phi1, phi2, phi3 etc. phi1, phi2, phi3 etc. These are all wave functions. These are all wave functions of 2pz orbitals, 2pz orbital of carbon atom. Okay, these are all 2pz orbital wave functions of carbon atom. Now, so using this, see, phi1, phi2, phi3, these are all taken from some selective basis set. So phi1, phi2, phi3 are all known. What we don't know is the coefficients. Okay, if you know the values of these coefficient, yes, you can find the wave function for the jth molecular orbital. Okay, yeah, so we are going to take this wave function as the trial wave function, because this is not the exact wave function. This is not the exact wave function for the molecule. We have LCAO is an approximation, right? So approximately we have constructed the wave function for a molecular orbital. Using that wave function as a trial wave function, we are going to calculate the energy of the jth molecular orbital using Huckel'S, using what is called the variation method. Okay, so the next assumption is that the average energy of the molecular orbital, right here, average energy of say jth pi molecular orbital, right, is calculated using the variational principle, variational method, using the variational method. Okay, the average energy of jth molecular orbital is calculated using variational method. Okay, yes, you know very well, average energy of jth molecular orbital, right, this let me represent this as EJ, average energy of the jth molecular orbital. Okay, we'll put this bracket symbol for average. So average energy of jth molecular orbital, which I am also going to represent as simply epsilon j. Okay, epsilon j means average energy of jth molecular orbital. How to calculate this? According to variational method, if we know the wave function for jth molecular orbital, psi j is known. How? From linear combination we can find the value of psi, we can get psi j. Okay, using psi j you can calculate the average energy of the jth molecular orbital. How? The average energy of jth molecular orbital equal to, I am writing in bracket notation, psi j, this is bra of psi j, and effective Hamiltonian for one electron, and ket of psi j divided by bra of psi j and ket of psi j. Right? Since this wave function is a linear combination of many atomic functions, okay, so if I use this here, depending upon number of functions that we combine, okay, you'll get several equations, or I'll give in the other way. See, if you use this formula, you will get the energy, but we have to minimize the energy for each coefficient. Okay, see, to minimize the energy with respect to the coefficient, what we have to do? Differentiate this Ej with respect to the coefficient Cj1, or let me write simply Cji. Okay, you can also write this simply as, since it is a summation, so I'll take summation. Okay, Cji phi I, right, where j represent jth molecular orbital and I represent number of electron. Okay, that is the ith carbon atom, right? So if I can go from I equal to 1 to number of carbon that is available, number of carbon that are involved in the conjugation, right? Now to minimize the energy, what we have to do? Differentiate this E with respect to the coefficient, with respect to each coefficient, and put that value equal to 0. If you put that value equals 0, you'll get an equation called secular equation. We'll get an equation called secular equation, right? Since we have many coefficients here, right? For each coefficient, if you differentiate and put the value equals 0, you'll get one secular equation. So number of coefficients is equal to number of secular equation that we get. Okay, then after knowing the secular equations, right, we can use matrix algebra to find the average energy of the jth molecular orbital, and we can also get the coefficients. Okay, those things we'll discuss in the next lecture. I stop here. Thank you.